Good morning, everyone. In the previous class, we were discussing about the dynamic logic circuits, and we saw what are the different problems associated with the dynamic logic problems, and we come up with some solutions which we can have to overcome those problems. But again, we saw some problem is also there if we are trying to solve some of the problems with the dynamic logic circuits. Okay, so this was the thing which we had discussed in the previous class. Now, till now, we have discussed all the logic circuits which are the combinational one. If I'm providing some input, so I will get some output after certain delay of that circuit. Okay, so if we ignore the delay of that circuit, in that case, whatever the input I will give, I will get the output immediately, and the output is the direct function of the input. Okay, so if there is some change in the input, there will be some change in the output as well. Okay, so those kind of circuit, we call them the combinational logic circuit. But suppose I have to store some data, I have to make some arrangement like feedback kind of arrangement. In that case, the second category of the logic circuits is the sequential logic circuit. So yeah, definitely in this particular lecture, we will start what is the sequential logic circuit, how it is different from the combinational logic circuits, and what are the different operating principles if we are going to operate, or if we are designing any circuit based on the like if we are designing any sequential MOS logic circuits. Okay, so let us discuss. Basically, as I told you, the logic circuits are basically divided into two categories. The first one is the combinational logic circuits, and the second one is sequential logic circuit. We can also call the combinational logic circuit, we can call them non-regenerative, because we are whatever the input we are giving, we will get the output immediately. But if I'm talking about a sequential, there is some feedback path, data can be stored for some for some instant of time, so that can be regenerated. So that is why the sequential logic circuit are also, we can call them the regenerative logic circuit. But if I'm talking about the sequential logic circuits, basically the sequential logic circuits are classified into three categories. First one is the bistable, second one is the monostable, and the third one is the astable. Okay, so let us discuss one by one what these all different types of sequential logic circuits are. Okay, so because if I'm talking about the bistable kind of sequential logic circuits, in that case, basically bistable means simply by its name we can identify there could be a two stable states. Okay, so if there are two operation modes or two stable states, and each of these stable states can attain with a particular input combination, then we can call them the bistable sequential logic circuits. Okay, how it could be, like the simplest example is the memory, like SRAM memory. What we can do, suppose I have the SRAM memory, I will explain in more detail about the SRAM, what is the SRAM, how it works. But for now, let me briefly explain how it works. So suppose I have a SRAM memory, we have two storage nodes. Okay, so if I am forcing to store one storage node with logic 0, then by default the another node will be logic 1, and vice versa. And we can have a two stable state, either 0 or it could be 1. Okay, so this kind of the sequential logic circuits are known as the bistable logic circuit, where we have two stable states. Okay, so based on the input, whatever we will provide, that output we can achieve, like whether it will be logic 1 or it will be logic 0. So this is all about the bistable. In detail, we will talk about the how it works, what are the operating principle, what are the different operating regions. We will discuss in more detail about the bistable, because in this particular lecture, our objective is to discuss more detail about the bistable. Because yes, latches, memories, SRAM, these all are the example of the bistable kind of sequential logic circuits. If we talk about the monostable sequential logic circuit, so in that case, what happened? suppose I have provided some input which can like by its name we can say like there will be only one stable state, right? So suppose I have given some input so that the circuit is activated or circuit is excited, and it comes to a certain level, certain stable state. But with respect to time, might be that level, whatever the state was there, that will eventually return to its a single stable state. Like, so this is what the importance of this monostable one is. So let me repeat it again what I'm saying. The monostable kind of sequential logic circuits are those circuits. Suppose I have excited somewhere, so I have excited the circuit. In that case, it will go to some logic level. It will change some logic, but with respect to time, the output eventually it will return to the single stable state, and so that is why we are calling it the monostable kind of circuits. Okay, monostable sequential logic circuit. Another one is the astable kind of logic circuit. Astable logic circuit means there is no stable state or there is no stable operating point that can preserve a certain time for that logic can be preserved for a certain period of time. Just like a simple example is the oscillator. Okay, so oscillator simply it oscillate between two ranges like maxima and minima. Okay, and there is no stable points. So those kind of circuits, we call them the astable sequential circuits. So the best example is the ring oscillator. What we do in the ring oscillator, we just connect all the inverters. So n number of inverters are connected, and the output of last inverter is connected to the input of the first inverter, and that becomes the ring oscillator. Okay, so later on we will discuss about how ring oscillator can be made, what are the different challenges associated with the ring oscillator. But for now, the example of astable sequential logic circuit is the ring oscillator. Okay, so this is all about the brief about different kind of logic circuits. Now let us discuss in more detail about the bistable one. So we'll talk about how it works. Yeah, so I just told you, suppose I have a combination logic circuit where we will be having n number of inputs, and we can have m number of outputs, and depends on what are the combination is inside, that will give you the different kind of outputs based on the input combination. So this is all about the combinational logic circuit. But if somehow we are able to connect the output of this combinational circuit with the input, in that case, that can become like, suppose we have a combinational logic circuit having some inputs, and then if we are able to connect the output of this combinational logic with the input side, so this can become the sequential logic circuit. Yes, very important thing is we are providing some feedback in this particular circuit if I'm considering the sequential logic circuit. Very important thing is the feedback could be unity gain, okay, or it could be something different. Okay, so the one combination could be we can have a unity gain feedback. So just like you can see in this particular figure, so just output is connected to the input directly, then it can act as a sequential logic circuits. The other combination could be like you can have a combinational logic circuit having some inputs and some of the outputs. But if I'm connecting the output with the input with the help of some element, feedback element, so this can also act as a sequential logic circuit. Okay, so this is not this feedback path is not necessary, it is the unity gain. Okay, unity gain feedback. So it could be anything, and if the arrangement is something like that, we can also call them the sequential logic circuit. Okay, so it depends what is your objective, what is your goal, and accordingly that feedback path is decided. Okay, so this is how we can call them the different classification of the sequential logic circuit. Okay, yes, this is really very important. Like, see, this feedback path which we have provided here and there, like in both the circuits in the bottom one, that can create some memory effect. Okay, what is that memory effect? Suppose I have connected the output with the input, because let us assume, let me write something. So suppose I have provided some input at t is equal to 0. Okay, I have provided some input at t is equal to 0, and I'm getting some output after certain delays, like t is equal to td time period. Let us assume after td time period, I'm getting some output. Okay, but let us assume, yeah, let me write it properly. So td time period, I will get some, where td is the delay of this combinational logic circuit. Fine. Now what happens? Because whatever the output we have received here, that is again feedback to the input side. So like in the next cycle, like t is equal to 1, like t dash plus 1 or something like, let me write it 1. Here basically, let me write properly. T dash plus 0. T dash is the initial time, initial condition. And here I am again writing t dash is the initial condition plus certain delay td of this logic circuit. So this is what at which output we will get the output. But suppose if I have provided the one of the output to the input again, so what will happen? This is the initial delay, okay, plus there will be some time period 1, like t plus 1. T plus 1 means the next cycle. I'm just simply considering the next cycle, that input will be considered from the output of this particular circuit. Okay, so what will happen with this time? We can because the same output we are connecting with the input, and it is storing or it is holding the data for the next period of time. Okay, so there could be some internal memory effect. Memory effect, it does not mean that there is always a memory element. It means that if somehow we can utilize the past value to the present value to get the future values, so there is some kind of the operation which is acting like a memory. Okay, so that is why we are calling it the memory effect. So this feedback path is just providing the memory effect in this particular logic circuit. Okay, so this is how these sequential logic circuits are important and how they are creating the memory effect in the circuit. Okay, so this is all about the logic circuits. Now the important thing is, as I just told you, the combination the bistable one is the important one which we need to consider, we need to discuss in more detail. Okay, so let us discuss the bistable circuit in more detail, and that is the let us see how this behaves. To understand the behavior of bistable element, what we need to do, we need to simply provide the feedback properly so that we can have a feedback loop in the memory effect. Okay, so suppose for to understand the behavior of bistable element, let us try to understand, let us consider we have a simple inverter, something like this. Okay, so suppose I have an inverter. Okay, and that inverter, let us assume this inverter is nothing but this is the I1. Okay, this inverter is I1. Now, if I have to make the feedback arrangement, so what I have to do, yeah, one more important thing is, like here, this is nothing but this is the input of inverter 1. So V input of inverter 1. Okay. Similarly, here we will receive the V output of inverter 1. So this is the VI1 and VO1 are the input and output of the first inverter. Now, if I'm providing some feedback, so let us see what I have done. I have connected an inverter in the feedback way, in the other way. Okay, and we are calling this inverter, let us assume this inverter is nothing but this is the I2. So this node which we have here, this is nothing but the VI2. Okay, VI2 is nothing but, like, if I have the inverter I2, so this particular node is nothing but this is the input of the second inverter. Similarly, if we talk about this node is nothing but this is the output of the second inverter, so VO2. But if we see clearly the figures, because this node and this node, these two are the same node. So Vi1 is same as the VO2. Okay, so let me write it here. So Vi1 is same as VO2, and similarly Vi2 is same as VO1. Okay. Now let us try to understand one very important thing. If we try to consider the characteristics of inverter, how it works, we know that suppose I have an inverter, and if I'm providing some input like a ramp, if I'm increasing the input with a proper step size, okay, so let us assume if I am increasing the input something like this, okay, with like a ramp, so the characteristics of the inverter looks like this one. Okay, so this is the simple characteristics how the inverter looks like, where this point is nothing but this is the VOH. Okay, this is, here we have the VOL. Okay, and here we have a threshold voltage of the circuit. So this is nothing but this is the threshold voltage at which both the transistors in a CMOS inverter is in the saturation region. Okay, so what we call it, yeah, so this is really very important to understand how the behavior looks like. So this is the input and this is what we will receive the output. So this is the input output characteristics of the simple inverter. Okay, so let us try to understand here. Suppose I am plotting the input output characteristics of the inverter number 1. Okay, if I am plotting the input output characteristics of inverter 1, in that case, what will be the input and output pattern? So input and output pattern will be something like this one. Here, this is nothing but this is the Vi1, and this axis is nothing but this is the VO1. Similarly, now let us consider the second case. If I'm considering the second case, like for inverter 2, so the characteristics could be something like this. Okay, so the inverter kind of characteristics we can observe again. Okay, so let us assume we are changing the input something like this, and we will observe the output something like this, whatever we had. And here this is nothing but this is the VOH, and this is VOL will be here, and here we will be having VTH of the circuit. Okay, VTH of the circuit. Now if you see here, the input output characteristics will be like this is the VI2 and this is the VO2. But here we have considered some of the we got some something like Vi1 is nothing but this is same as the VO2. See, this is the characteristics for inverter number 1. This is the characteristics for inverter number 2. Okay, but if we try to match the axis, because if we see here Vi1 here is in the x-axis and the VO1 is in the y-axis. Similarly, Vi2 is in the x-axis and the VO2 is in the y-axis. But if we try to match complete circuit, complete bistable circuit, then what we will see? We will see here Vi1 is same as the VO2. Here Vi1 is, if you see, Vi1 is here, okay, and VO2 is here, which are same, but the axes are different. So we need to match the axis. So if we will match the axis, so what I need to do? I need to simply rotate this graph, whatever this graph is, by 90 degree in this direction and again 180 degree in this direction. Okay, so just flip in the both direction. Like once I need to flip in the counterclockwise 90 degree, then we can make the axis, and then again I need to vertically I need to flip it. Okay, so after flipping these things, we will get like let me make it here. So suppose I have a two transfer characteristics of both the inverters, and which we saw, which will look like this one. So here, if I am flipping all the components, whatever we just said, then how it will look like? This is nothing but this is the VI1 and this is same as VO2. Okay, so we are making like this, and the y-axis, this is nothing but this is the VO1 is same as VI2. Okay, if we are able to make like this, so let us try to draw the characteristics how it will look like. Okay, so let me draw it. So the characteristics will look like, yeah, so if I'm changing some input, so let me draw it properly. Okay, so this is, let us assume this is the input change. Okay, and the output we can observe something like this. Okay, so let us assume this is the output behavior. Okay, so this is the output behavior of one of the inverter, but if I need to change the scale, so the second inverter behavior will look like this one. If both the inverters are perfectly matched or same sized, then the behavior of second inverter will look like this one. Okay, so this is how we can match the input and the output one. Now let us try to point out some of the things which are important. If we see here in the previous circuits, whatever we have drawn the characteristics here. In these characteristics, if you see, if I'm considering this particular node, because at this node, the inverter will have a particular logic. So there is no uncertainty. It is a fixed logic. Okay. So this node, we call it the stable node. Similarly, if we talk about this logic level is also a stable logic level. Okay. Stable logic, so if any of the circuit is giving the characteristic something like logic, this particular logic, what it means, it is stable at logic 1. Similarly, if one of the inverter or any of the inverter which is giving this particular logic, so we can call them it is stable at logic 0. Okay, but if we see during the transition, like at this particular point, we know that both the transistors are in saturation region, and the uncertainty is more here because the gain is very high. So this is the point where we can achieve the maximum gain if I'm considering any of the circuits. So the point at which like input and output characteristics are crossing to each other, at that point we will get the maximum gain. Similarly, the point where the logics are fixed, at this point and at this point, the gain is minimum, and if gain is minimum, so we can call them the stable points. Okay, so and similarly that will happen with the second inverter as well. So this point and this point, these 2 points are the stable point, and this point is the unstable point. Okay, the important thing is, if I'm considering the stable point, at the stable points, the gain is minimum, it is less than 1. Okay, so we know that there is some point, at this point we can achieve the unity gain point. Similarly, here at this point we can have a unity gain point. Before that the gain is less, and after that the gain is higher. So gain reduces before this unity gain point, and gain increases after unity gain point. Okay, so if we consider this node, this particular point, at this point gain will be less, or it will be less than 1. Okay, similarly, if I'm talking about this node, at this node as well, the gain will be minimum, or it will be less. But because if you see here, this is the point where both the inverters are touching to the input one, like they are crossing, and at this point both the transistor in a particular inverter will be in the saturation region. Okay, so yes, now if you consider this point and considering both the characteristics, VTC characteristics of both the inverters, so this is the point where all four transistors are in the saturation region. Two transistors from the I1 and two transistors from I2, and all the four transistors will be in the saturation region at this particular node. Okay, and at this node we will achieve the maximum gain. Okay, so the gain will be greater than 1. So let me write few things which is really important. So at this point, gain is less than 1. At this point again, gain is less than 1. Okay, at this point we will be having gain greater than 1. At this point the gain will be greater than 1. Okay, so this is the important thing. And if I'm talking about the stability kind of things, so the point where the gain is minimum, at this point we can call them the stable point. This is nothing but this is the stable point. Similarly, this point is the stable point, and this point is the unstable point. Okay, so this is how we can match the input output characteristics of two inverters if I have connected back to back. Okay, so this is really important. Now the very important thing is, so we got to know that, like, if I have connected two inverters back to back, in that case I will get a characteristic something like this, and this kind of characteristic we call it the butterfly curve of any sequential circuit. Okay, so this butterfly curve basically indicate how much stable the circuit is. Okay, so stability is decided by this butterfly curve. Later on we will check how we can understand the or how we can calculate the stability of any circuit by considering this one. So this is important. I will tell you in more detail if we will talk about the SRM cell. There we will discuss about the butterfly curve, stability, and other things. Okay, so yeah, one more thing I just want to include here. The point where we are crossing like this, here I am assuming the gain is 1. So, and here also gain is 1 at this point. Okay, so this is how we can make it. Now, one very important thing that we should consider here is, what is that important point? Important point is, suppose I have an inverter, feedback inverters, two feedback inverters, and we are getting two stable points and one stable point. In that case, what will happen? The point at which the circuit is giving the stable characteristics. Yes, one more important thing. Before I move ahead, let me explain one more thing here. If you see at this node, let us assume this green characteristic is for the inverter number 1, and the second characteristic is for inverter number 2. Because if you see here, if this point is the stable one, this is the stable one, because we have a two stable points at logic high and at logic low. Similarly, there are two stable points in logic high and logic low for the second inverter as well. So if we see here, at this point, both the inverters will be in the stable state, because this point is stable for logic high for one of the inverter, and stability or stable for logic 0 for another inverter. Because see here, this is the characteristics for the first inverter, which is for logic high, and this is the characteristics for the second inverter, which is giving logic low, and we are connecting. Yeah, we are superimposing at the same point what it means, the both the inverters will be at the stable one, but one will be for logic 0 and the second one will be for logic 1. Similarly, at this node, if we see, this is the point where the inverter 1 is giving logic 0 stability, and the second inverter is giving logic high stability. So we can call this the stable point, and logic 0 and logic 1 stability for both the inverters based on their characteristics. So this is important thing. Now let us try to see what happens with the energy if I'm talking about the different stable state and the unstable states. So see, stable states means what? If any logic is in the stable state, in that case, the energy will be minimum, like the stability is more, it cannot be excited easily. Okay, so a less energy is there, potential energy is very less at those points. Okay, and at the unstable points, the potential energy is very high, or it is maximum, so that the characteristics can change something like this. So let us try to make some characteristics for the energy one. Okay, so we know that this is the point where we are getting the stability one. So this is nothing but we are matching with the same axis. Let us again matching with the same point. So same point is here, and also, yeah, let me use this another color here. So at this point, we can have this one. Okay, now let us try to draw the circuit. The point where the circuits are in the unstable state, at that point we will observe the maximum potential energy, or the maxima will be there. So the characteristics will be something like, yeah, this is the minima, and this is the minima, and the characteristics will be something like this one. Okay, so this is important to understand. So this is the energy. Okay, and here I have one maxima. Okay, and we can have a two minima. One is here and another one is here. So two minima. Okay, so this is how it is important, like how the energy is maximum and minimum. Okay, so this is how we can understand. Yeah, I think there is some change in the color, I don't know why, but yes, I think if I will save it, might be it will be the same what I'm drawing. Okay, so this is how the bistable element and its behavior will look like where the gain is minimum, where the gain is unity, where gain is maximum, and based on the gain we can decide which of the point is stable and which one is the unstable, and similarly based on that we can consider where we will observe the maximum potential energy and the minimum potential energy. Okay, so if I have a bistable element where we have a two stable point and one stable point, in that bistable kind of circuitry, we will observe one maximum energy node and a two minima energy node, like so where the energy will be minimum where the two stable points are. Okay, so this is important to understand. Now let us go into more detail about the behavior of bistable circuit. Okay, so how it will look like, let us try to understand in more detail. In the previous circuit, in the previous page, like if you see here we draw a bistable element by connecting two inverter back to back, where the input of one inverter is provided to the output, or the one of the output is connected to the input, and the vice versa, right? So the input and outputs are matched in the forward path and in the feedback path. Okay, and this is how this looks like. Okay, so if we consider the same circuitry, And if we try to open up this circuit, then how it will look like? Because we have a two inverter, I1 and I2, and we know that we can make this inverter by simply PMOS and MOS transistor. Like, so I just wanted to explain you how this CMOS based bistable circuit we have. Okay, so let us try to understand that one. So CMOS bistable element, suppose I have a simple inverter, something like this. Okay, and another inverter I have like this, where this is the input for this one, this is the output. Similarly, this is the input and this is the output. What I have to do, I have to connect the input of one inverter to the output of the second inverter, and vice versa. Okay, so if let us try to connect something. So here what I have done, what I have connected, I have connected the output of this inverter with the input of this inverter, and the second possibility, like the input of this one is connected to the output of this one. So if somehow we are able to connect something like this, then we can call it the bistable circuit, like CMOS based bistable circuit. Okay, so let us try to see how it will look like. Okay, so let us try to write some notes where we have. Okay, let us assume the left side one is the inverter number 1. Okay, so if this is the inverter number 1, in that case, like this node, this is nothing but VI1. Okay, this is the VI1. This is the VO1. Okay, and this node is nothing but this is the VI2 and VO2. Okay, so this is how it will look like. Now let us consider the circuit is in the unstable state. Okay, unstable state means what? Like if we see in the previous slide, we studied about here what we studied. Here we studied like at the point where both the transistors in a single inverters are in the saturation mode, like in the saturation region. In that case, we can call them the unstable point. Okay, so now, and if both the inverters are in the saturation, like all the transistors are in the saturation region, the output voltage of both the circuits will be nothing, it will be close to the threshold voltage of the circuit. Let me repeat it again what I'm saying. Yeah, so let me explain from here is this circuit. If you see this circuit, at this particular point, both the inverters in both the transistors in inverter 1 are in the saturation region. And if both the transistors are in saturation region, the output we will observe, and that is equal to the threshold voltage of the circuit. This is not the threshold voltage of the transistor. You should remember it, right? So this will be is equal to the threshold voltage of the circuit. Similarly, for the second input, if both the transistors are in like for the second inverter, if both the transistors are in the saturation region at this point, the output which we will observe, that will be equal to the threshold voltage of the inverter or threshold voltage of the circuit. Okay, we can also call this the switching voltage at which the transistors are switching. But the important thing is, if somehow I move this unstable point somewhere here or somewhere here, might be the gain will be changed. And if the gain is changed, if it is moving in this particular direction, what it means, the input VI1 is moving towards to the lower side. Okay, so the output will move towards the higher side. So we can make them biased towards a particular logic. Let me repeat, this is really very important, especially if we are designing the digital systems. Suppose I'm considering both the transistors in a single inverters are in the saturation region at node where we are getting the VTS output. Okay, but if forcefully, if I'm changing this voltage either towards the left side or towards the right side, in that case we can make the transistor biased either towards to 0 or towards to the 1. Okay, so if forcefully I have made something like this, where I can get the, like this VTH is moving towards to this one, so the first inverter will become stable high, and the second one will become the stable low, and the vice versa. Okay, so this is really very important to understand what I'm saying. Okay, so to demonstrate this one, let us try to understand. So here we have the combination. Now suppose either I can have a VOH, VOL, and the VTH. We have the three possibilities. So with respect to time, initially, let us assume, let me make the axis. So this axis is nothing but this is the VOL. This is the VOH. And this is nothing but what we are calling the VTH. VTH is nothing but the threshold voltage of the circuit. Okay, so here we have three things. Initially, let us assume at t is equal to 0. Okay, at t is equal to 0, all the transistors are in the saturation region. If all the transistors are in saturation region, in that case, the output which we will observe will be just like this one. Okay, so this is nothing but this is the output which we will observe. But suppose forcefully I am changing this VTH towards the left side. Left side means what? Inverter 1, the input of inverter 1 is moving towards to the logic 0 side. If it is moving towards the logic 0 side, output will start moving towards to the higher side, like VOH side. So in that case, the behavior of this inverter will start moving like this. Okay, so yeah, so it will not be like a linear, but yes, it will be something like this. Okay, so this is nothing but this is the behavior of VO1 if the unstable point is moving towards to the left side, or by considering inverter number 1 if it is moving towards the left side. Okay, similarly the second thing can happen, like with the same conditions, because both the inverters are connected to each other. So another set could be, it will look like this one. So the second inverter will give the characteristic something like this, and this is nothing but this is the VO2. Okay, so this is how both the inverters can behave, or that can switch into the stable points if I am exciting, or if I am giving some input to some of the inputs. Okay, so this particular lecture is really very important to create the fundamental of memory design. Okay, so you should understand like how we have connected two inverters back to back to make them a feedback path, and how we are exciting the inputs so that the output will be changed to a particular logic from the unstable point to the stable point. So at this point, this is the nothing but this is the unstable point. Okay, so both the inverters are in the unstable state, like this is the unstable state. But once we have excited some input, we have provided some force to some of the input, in that case either in the positive direction or in the negative direction, accordingly the logic will be changed, and this is the node, this is the point where we will get the stable characteristics. So both the inverters will be in the stable state. So if I'm talking about the VO2, like VO2 is nothing but this is the output of the second inverter, and output is close to logic 0, and if it is at logic 0, what it means, the input is at logic 1. So this transistor will be in the on state, and this transistor will be in the off state, and similarly this transistor will be in the on state and this transistor will be in the off state if the conditions are like this, whatever we have made in this particular circuit. Okay, let me repeat it again. This is nothing but this is the inverter 2, and let us assume this is the inverter number 1. Okay, initially let us consider all the transistors which we have placed here are in the saturation region. So at that point, the output will be close to the VTH. But suppose I have excited some of the input, like input 1 is, let us assume input 1 is towards the left side. Like left side means what? Here, let me go back to that slide. So left side means what? Initially we had at this point, but I am changing here. So if I'm changing input in the left side means simply I'm changing here in this side direction, right? So if somehow I am doing like this, so in that case, the output behavior will be it will switch towards the high logic high side. And if it is switching towards the logic high side, what it means, the pull-up network will be responsible in the inverter number 1. Okay, so this transistor will be on, this is off, and vice versa for other things. So if we see here, 2 transistors are in the in on state and 2 transistors are in the off state. So one PMOS and one NMOS is in on state, and one NMOS and one PMOS is in the off state. So this is really very important. Like what we have done here, we have done, like we have provided some change in the input of any of the inverter, and accordingly we can get logic 0 or logic 1. So one of the output will store logic 1, and the second output will store logic 0. Okay, so this is how forcefully we can store the data and memory. So this is the basic building block to create the static random access memory. Okay, so in detail we will discuss again about this circuit, and we'll get to know how this circuit, we can operate this circuit, and how we can excite this one. Okay, so only, like, see, the important thing is we are using, or we are utilizing an external source to excite this circuit towards a particular logic, like biased towards logic 0 or logic 1. Okay, so we are providing some input, but here we do not have any arrangement which can provide the external input. So for that purpose, we need to add some of the more transistors while designing the memory. How to add that one, I will tell you in detail later on.
Sir, one question.
Yes, please.
Sir, question is that in stable state, sir, whether it will work as memory or in unstable state.
Yeah, it will act as a memory if it is in the stable state. Why it is so? Because see here, VTH is nothing but this is the switching threshold voltage of the logic. Okay, initially the circuit was in the unstable state. So to make it as a memory, we need to make them into the stable state, so that they can store a particular logic for longer time period, unless we have not removed the supply voltage. What is the role of supply voltage? I will tell you. So it will act as a memory if it is in the stable state.
It means that more the stability, more the
yes. Yeah, like the robustness will be better. Okay, and that stability is calculated with the butterfly curve which we have drawn in the previous slide, and how that butterfly curve impact on the stability we will discuss in more detail when I will discuss about the SRAM cell. Okay, so please wait, these points will be repeated again. Okay, and then you will get to know about the stability and other things. Okay, so that is really very important.
Hello, sir.
Yes, please.
Sir, this first both were at both inverter were in saturation state, so output was VTH. So yes. From that point, like how is the output VO1 increasing? Means that VI.
Yeah. So what I'm saying, suppose if somehow VI1 was like, see here, VI1 and see the previous circuit, then the previous diagram, then you will be able to understand here. If you see here at this point, let me use the laser pointer. At this point, if you see, this green curve is for the inverter number 1, and the purple one is for inverter number 2, right? And at this point, all the transistors are in this saturation region. Is this correct? Okay. And if you see this point, at this point, input is also same like the output. So important thing here, input like VI1, VI2, VO1 and VO2 all are equal. Okay, so all are equal. Now if I have to make them biased towards particular logic, so I need to forcefully change any of the input. Okay, so if I am changing this input 1 towards the left side, what it means? It means I am making I1 lower than the VTH1. And if I am able to make I1 lower than VTH1, so the output of the first inverter will become stable towards the logic high. And similarly, because these are we are matching the axis, so the second transistor, second inverter will be in the opposite case. Okay, so this is how we are making them stable and unstable point. You got the question answer?
Yes, sir. So means, sir, we are decreasing VI1, right?
Yes, so forcefully we are decreasing VI1. Either we can decrease the VI1 or I can decrease the VI2. Based on that, or I can increase the VI1 or increase the VI2, and based on, like, we have the 4 possible combination. First combination is like I can increase the VI1 or decrease the VI1. Second combination could be I can increase the VI2 or I can decrease the VI2. So based on all these 4 possible combination, one of the transistor will come into the logic 0 such stable state, and the second inverter will come into the logic 1 stable state, and accordingly they will switch the logic. Okay, so this is how we can force this input to a particular state, like logic low or logic 0, that I will explain in more detail when I will talk about the memory SRAM. Okay, the point is clear, or is still there is some doubt?
No, sir, it is clear.
Okay, fine. So one thing I just wanted to complete it in 1 minute, and then yeah. So this is what we have understand how we can make them the stable one. Yeah. So let us try to make the phase plane representation. How it can be done? Suppose this point is nothing but, yes. Let me write few things. So let us assume this is the VOH of one of the inverter. This is the VOL. This is the VOL of the second inverter, and this is the VOH of the second inverter. Okay, and if we talk about the step, these points are nothing but this is the threshold voltage of one of the inverter. So let us assume this x-axis is for the inverter number 1 and the y-axis is for the inverter number 2. So this is the VOL, VTH, and VOH for inverter number 1, and similarly this is VOL, VOH, and the VTH for the inverter number 2. So if you see this point, at this point, okay, this point is nothing but this is the stable point. Okay, this is nothing but this point is the stable point which we are calling. But if I'm changing the input towards to this side, in this particular side, then one of the node will become the stable one, like this will move towards to the VOH. And if I'm changing in the positive side, like if I'm increasing, then it can change towards the next stable state. So we have this one stable state, and one stable state is this one, and this is what the unstable state is. So this is how we can represent. Yeah, this is quite easy. This is the same like what we have done in this middle